topological spaces. It's really a question of where that Hom lives. And in the elementary case, we start out by thinking of the Hom as being a set and living in sets. But again, that's a kind of question of foundations. So it's kind of a relative thing. Should I do one more? Yeah, I have a minute. Let's do one more because then I will cash this check. I'll do that one. So I want to show that A cross B plus C is isomorphic to A cross B plus. So it's the distributive law, right? A cross C. So in fact, in any Cartesian closed category with sums, products distribute over coproducts. It doesn't have anything to do with the exponents, right? We said that we're looking at distributivity of products over sums. If we know that there are exponents around in the Cartesian closed category, it forces the products to be distributive over the sums. That's kind of funny, isn't it? That actually is a special case of a more general fact that we'll meet in the next lecture. It's because this operation of taking product with A is a left adjoint. The exponent in a Cartesian closed category, it has a right adjoint. So this operation is left adjoint to this one. And adjointness is exactly this, that maps out of this one correspond to maps into that one. And now it's a general fact that left adjoints preserve coproducts. So this is saying that this left adjoint preserves the coproduct. And that's how I teach my kids the distributive law for arithmetic. So first we learn that left adjoints preserve coproducts. OK, so we want to show that. So we have to show, we'll use Yoneda. So we have to show that Homming into this thing, should I Hom into it or should I Hom out of it? Let's Hom out of it. So we'll use the same argument, but we'll dualize everything. We use the theory of duality, right? We do everything over C op rather than C, and we Hom out of this thing. So we Hom A cross B. Remember, I told you that this principle of duality is a pretty slick business. So here I'm using it, and I don't really have to think much about it. I can just do it formally. In fact, all of these calculations are purely formal now that I've built the machine. So that's what I'm trying to show. And I'm Homming out of that. And I need to show that I can get this isomorphism. But this thing now I know is Hom B plus C x to the A. And now I pull the coproduct out on the left. And now, let's see, do I just put them back down? Yeah, I just put them back down. A cross B x, yeah, that's it. And now I can push the coproduct back in on the left. So there we go.
Second step on the derivation on the left, are you using this back?
This one?
Second step.
Right here.
Oh, yes.
Right here.
Yes.
Yeah, you didn't hear me say that?
Oh, sorry, yeah, I messed up.
Yeah. I said here, I said, oops, I did the exercises in the wrong order. I should have done that one first and then this one. So I said, give me this for now, and I'll complete it, and then I'll owe it to you. So that's what I did right here, and now I just cashed the check. OK, so there's something else that I wanted to say, but of course I don't have time to say it, but I'll just mention it, and then I'll say it next time. And that is, it's good to know that this Yoneda embedding has some if the category C is known to have some structure that you're interested in, it's good to know that the Yoneda embedding preserves it. So, for example, if C has finite products, then the Yoneda embedding of C cross D, well, what's that? That's Hom blank C cross D, but we just checked that that's Hom blank C cross Hom blank D. Right? That was one of our rules. It's this one. The products pull out on the right. So that tells me that the Uneta embedding itself preserves products. So I have to talk about this a little bit next time, but the Uneta embedding preserves products. Moreover, if this is known to be Cartesian closed, the Uneta embedding preserves exponentials as well. It preserves all the Cartesian closed structure that exists down here. So if this is a Cartesian closed category, then this functor preserves all the Cartesian closed structure up to here. I haven't shown you yet that this thing is Cartesian closed. I'll do that next time too, okay? And that this preserves it. But what that tells us is that we then have a model of any lambda theory that's modeled in this Cartesian closed category gets a model up here which satisfies all the same sentences in the lambda calculus, that is, all the same equations of lambda terms, and habitation conditions on types that are satisfied down here. And from that, we can infer a completeness theorem for the simply typed lambda calculus with respect to these very special models of this Prisci form. But we'll do that next time. Thanks.